Hello everyone. We're going to talk about thermal expansion today. Thermal expansion is what happens when you heat something. You increase the temperature of that material. Okay. Um, you might say opposite of that will be what happens when you cool something and you decrease the temperature. You can say thermal shrinkage or compression. Uh, but we use thermal expansion for both of them. Even if it doesn't expand, if it shrinks, it still is negative expansion. All right. A simple thing will be I have an oven. So this is some oven, say at temperature T1, some temperature T1, and I put a bar and it's got some length L1, and of course got some cross section. I'm not worried about cross section right now. I just want to look at the length. All right. Now I increase the temperature of the oven, and I find that this temperature went up to say T2, and length went up to this much. So this is delta L. So delta T is T2 minus T1. Well, how much it increase depends on how long a bar. I have a longer bar, I'm going to have more. It's almost like the same idea as we had strain, right? So if you if you remember in the strain, we had the percentage change in length, and that turns out to be also the right idea here. So you might say thermal strain here, or strain. So strain here will be idle length L1 and a change by that. So that's going to be delta L over my original length L1. So we can just write an L1 here. In the books you will see just L written down. That's okay, as long as you know you're dividing by the original one. It's a percentage of the original length. All right, so this is the fraction. So this is strain, which you can write a symbol epsilon for it. This strain is delta L over L. I'm going to drop one from here, consider now, writing now. So this is actually proportional to how much temperature you increased or decreased. If you increase the temperature, this is positive. If you decrease the temperature, it's negative. And for different materials, say you have an aluminum bar, you'll have one amount of strain for this. If you had maybe a plastic, it will have a different amount. Then you had brass. So every material you can go out and actually tabulate at what rate this is changing, and that you can just multiply by that rate for that material. So this is material dependent coefficient of expansion. This is called coefficient of thermal expansion. And we are doing with length only, so it's called linear thermal expansion. So what are some of the values? Okay, so I have some table here. For instance, aluminum is for alpha for aluminum is 23 times 10 to the power minus 6, and you can see it's can only, this has no units, so this one is 1 over temperature. If this is in degrees Celsius, this is per degree Celsius. All right. So if you want to get per degree Fahrenheit, what would you have to do? Well, if you remember, F over 32 is C minus 5, C over 5. This is the whole thing, 32 over 9. So remember that. Then delta F over 9 will be equal to delta C over 5. You can say that, compare this for F2, 32 over 9 minus C2 over 5, and F1 minus 32 over 9 equals C1 over 5. And then you take as difference, you get this, the difference of these guys and difference of these guys, you get that. So 32 over 9 kind of cancels out as a common factor. So I know this is that kind of stuff, right? So per degree Celsius will be 23 times 10 to the minus 6 time. So if I increase Celsius by, if a temperature 1 degree Celsius, remember, this was the expansion in the mercury, 1 degree Fahrenheit will be smaller increase, right? So it's going to be 5 over 9, right? This is going to be 5 over 9 per degree Fahrenheit. Because you remember that if you keep this thing in mind, you will be okay. So in Celsius, you have a 0 degree here, 100 degree, and you have 100 parts. And this is 212 and 32, but you have 180 parts. So if this was this is, so this was 1 degree Fahrenheit. So say this was 40 and this is 41. So mercury would rise this much, right? But if I do the same thing, starting here, that will be, so this was, say, some x plus 1 degree Celsius. So you can see you have increased the temperature more. 1 degree, if you increase temperature 1 degree Celsius, that's actually more increase than 1 degree Fahrenheit if you increase. Okay. So this is stability per degree. Sometimes we need per degree Fahrenheit, and it's not just using F minus 32. It's actually using just 5 or 9. Okay. Let me look at some numerical examples we can work out for thermal expansion. Okay, let's work out a numerical example for thermal expansion. I have 2 rods, 1 meter each. One is aluminum, one is copper. At room temperature is 27 degrees Celsius. I put in the oven, a 227 degrees Celsius oven. This is the coefficient of linear expansion for the 2 materials. So remember, the alpha depends on the material. Alpha depends on the material. And you want to know what's the expansion of each one of the bars. It's pretty straightforward. Remember that delta L over L, that's the strain, is alpha times delta T. So I'm looking for delta L, so I'll say delta L equals to L times alpha delta T. L is the original length, and so for the 2, I'm going to get a different answer. For aluminum, I'm going to get this 1 meter times alpha is 23 times 10 to the minus 6 meter, and the difference in temperature is 200 times 200 degrees Celsius. And this is meter. This is per degree Celsius. So this per degree Celsius and degree Celsius, they will cancel out. So this is interesting, this per degree Celsius, and this also change in temperature. That's what's canceling out. I wish we had a way to write it differently, but that's the way it's written. You can say I got multiply this, you get a 46 times 10 to the power minus 4, and which will be 4.6 times meter times 10 minus 3 meter, which is 4.6 millimeter, which is approximately half a centimeter. So that's how much aluminum will expand. Now copper has a lower, that means it's going to expand less. Again, I don't know if you have experience with both these materials, but it kind of makes sense to me. Is 1 meter times 16.5 times 10 minus 6 per degree Celsius times 200 again. This cancelling out, and so this double of that was going to be, and so this will be 3.3 millimeter. So we have a different answer for copper. Okay, we just talked about how length expands, but we ignored what the cross section was going on, right? We just looked at the length expansion, and you can study the area expansion in the book, but I'm going to jump over that and I'm going to study what is volume expansion. It turns out volume expansion of gases is a different deal than volume expansion of liquids and solids. All right. We can make our task even simpler. Look at a cube, and see how the volume will expand. It turns out you don't need more than linear expansion. Those listed linear expansion alpha, that's all you need. Okay. So if you have a solid, that's all you need. But if you have a liquid, you will have a separate table of volume expansion coefficient. Let's see. So if I have, and I'm just going to take a cube, so there's same length. Right? Length, width, and height are the same L. And when it expands, the length will expand by delta L. Height will expand with another delta L. So delta L, and this width will expand to another delta L. So you are going to expand delta L in all three, like delta L. So if you look at the new volume, change in volume will be new minus old. And so you have L plus delta L cube minus L cube, that's the volume. Now we expand this, is going to get L cube plus 3 L square delta L plus 3 L delta L square plus delta L cube. I didn't mean to send you to high school, but this is just expansion, cubic expansion, L cube. So that's the change in the volume, and you can cancel this guy out. What we are interested in, the strain, right? How much is it strained? So I'm into delta V over V, which is L cube. So divide by L cube. So this is 3 delta L over L. Or 3 times delta L over L, and the other one is 3 delta L over L, the whole thing is squared, and this is delta L over L cube. delta L over L is small, less than 1, okay? So, it's a very small percentage of the full thing that changes, right? So if you square it, it's getting smaller. The cube is even much smaller. So these, compared to that, are negligible. So what's left is delta L over L. But we already know the law for that. Right? Delta L over L, we know already. So we can just write that down here. So I have a delta V over V is 3 times delta L over L. But this is nothing but linear expansion. So volume expands like 3 alpha, 3 times alpha delta T. So this one is delta like that. And this for the material. So this volume strain, if you say I am going to say this is equal to some beta delta T. So I'm going to invent a new coefficient to tabulate my volume rate at which volume expands. Not time rate, but fraction of the strain of the volume expansion, okay? This is the strain of the volume expansion. So this is also called bulk strain. Then this will depend on material, and this is the bulk, kind of like a bulk modulus kind of stuff. You might see familiarity with that. This whole idea is developed in very similar to the other idea. So this is bulk coefficient of thermal expansion. And you can see the beta will have to be equal to 3 alpha. So beta equals to 3 alpha. Just from this. And alpha is pretty well studied for solids. So you might say, I don't want to study solids, liquids, but for solids is just this. For liquids, you just go directly here for the liquids, because you don't have a length of a liquid well defined, right? Because the length is not well defined concept, but the volume is, and so you work with the volume. So that's why I had lumped them together as one uniform concept. But you can see that for solids I can actually use the linear expansion. For liquid I have to go to a table of liquids. For instance, if I had acetone, so alpha for say aluminum was 23 times 10 to the minus 6 per degree Celsius. Beta for acetone is considerably larger, by the way, and it's like 1.5 times 10 minus 3, I guess. Yeah, 1.5 times 10 to the minus 3 per degree Celsius. Like a 3 of, if you make this 2.3, make it 5. So it's like a 2 orders of magnitude, right? And if you get the beta for, like using this, beta for aluminum, it will be 3 times that, times 10 to the minus 5 per degree Celsius. And from here to here, so it's about 50 times, right? About 50 times. Acetone volume will expand about 50 times more for the same change in temperature than aluminum will expand. It also makes sense because more expandable. That's what I say. Liquids are in general more expandable. The water is, I'm looking at water is 0.2. For beta for H2O is 0.2 times 10 to the power minus 3 per degree Celsius. So this is like 2 times 10 to the minus 4. So what is expandable more than aluminum? That would be, of course, this is a liquid water. It's in the range of 0 to 100 degrees Celsius. So this expandable. I don't have a list for what the ice is, but you can look it up online. You can do numerical examples, but it's really concept which is more important here. Okay, so take care.